Alrighty, hello and welcome to episode 2 of season 2 Chemistry Chats with Cochrane. Today we are looking at gas calcs, using the basic gas calcs with stoichiometry, and then we're going to follow on with looking at some more complex calcs with stoichiometry, and then episode 3 will be complex calcs with mixed stoich. So let's have a look at what we've got here. We've got a couple of sample questions here. What volume of water vapor is produced if 17.56 litres of hydrogen is reacted in excess oxygen at STP? So a couple of key things we need to highlight first. Stick with the theme, I've been doing it in red. So essentially, we are trying to calculate, the thing that we don't know about here is the volume of H2O, really specifically as a gas. That is what is currently unknown to us. We are told here that we have a volume of hydrogen that is known to us. Volume of H2 is equal to 17.56 litres. And we also know that this bad boy occurs at STP. So with that in mind, we need to write ourselves a chemical equation. How do I know I need to write myself a chemical equation? What have I done in order to work that out? Well, this is what I've done. I need to calculate a volume of water vapor. The key word is in the question here where it says is produced. Whenever I'm thinking the word is produced, that means there has been some kind of reaction. And given the fact that this question does not provide one, I need to write that. It also tells me that hydrogen is reacted in excess oxygen. And so that means there is the two reactants of hydrogen and oxygen. So let's go ahead and write that equation. H2 plus O2 we know produces water. It's a simple combustion reaction. In fact, produces two water molecules and requires two hydrogen molecules to do it. Now, please note, I have not included states in this equation because all it is for me is a stoichiometric ratio, so that doesn't really matter. Now that I have written my equation, I can simply calculate my number of moles of H2 by saying that number of moles is equal to V on 22.71. How have I isolated this formula? Because our reaction is at STP, so I've copied that straight from my data sheet. I've then said that my volume is equal to my number of moles is equal to 17.56 divided by 22.71. If I chuck that in a calculator, I get a nice simple number of 0.77 moles. Part 2 of this then, I now need to use the nuke to calculate my number of moles of water vapor. So I would say the number of moles of H2O is equal to the coefficient in front of H2O, which is 2, divided by the coefficient in front of hydrogen, which is 2, times by the number of moles of hydrogen, which is 0.77. And I like to put a note down here that I am using stoich to do this. I didn't know this, but stoich is from How to Train Your Dragon. This whole time people laugh at it, and I thought it was funny, but actually it's just funny because it's a movie quote. So 1 times 0.77 is, of course, 0.77 moles of H2O. Now, of course, the actual question is for volume, and we know it's at STP, so now we can say that volume is equal to, we need to rearrange our equation, is equal to 22.71 times by N, which in this case is 0.77. Chuck that in the calc. What do I get? 17.56 litres. There's our answer. Done and dusted. Now, next question here, what volume of oxygen gas is required to react with excess hydrogen to produce 254.5 litres of water vapor at STP? Again, it's an STP calc, so it's simple. We do know it is a stoich calc because we are seeing this word react, and we have seen the word produce, so we know that this is a chemical reaction. So we've already written the equation, but we'll write it again, pretend it is a whole brand new question. So 2H2 plus O2 produces 2 waters. Get those two bad boys together. I've now got to do a little bit of quick calcs, and that is by starting off with my volume of water. Would you agree with me that the volume of H2O, as recorded in the question, is 254.4 litres? Easy, Dunskies. I also have here that I am trying to calculate the volume of O2, which is currently unknown. So let's go ahead and start with our number of moles of H2O, which is equal to V on 22.71, which in this circumstance is 254.4 divided by 22.71. And if I chuck that in a calculator, I get 11.21 moles. Now, a couple of things that I really want everyone to notice in the way I've set out this answer. I've included what I am talking about in each different circumstance, right? So I've said volume of this and volume of this and number of moles of this, because remember, what is our feedback from the last examination? numbers often appear in the answer without any context and without any explanation. So there we go, we've got our number of moles of H2O. We are now going to calculate our number of moles of oxygen by using the nuke. The coefficient in front of oxygen is of course 1. Coefficient in front of H2O is 2, multiplied by the number of moles of H2O gives me the number 5.603 moles. Now, please note, I have set this out in this circumstance as going across the page like this, start here and then move across. That is fine. It's also okay if you go downwards, whatever is going to make most sense on the paper. But just be really clear with your marker that they can follow your working and where you're going. Don't start at the top here and finish down here without really clearly indicating how it is that you got to where you're going, all right? If you're going to do a weird order, make sure it's really, really clear and easy to follow. Cool, so we've got a number of moles of oxygen is half of 11.21, which is 5.603 moles. Our final step then is to calculate our volume of oxygen. We know that from rearranging our equation, that volume is equal to 22.71 multiplied by the number of moles, which in this circumstance is 5.603. And that will give me 127.25 litres, specifically of O2. Beautiful. So we can see that stoichiometry with simple gas calcs, very similar to what we have already covered, but just using different formula. So that is that guy done and dusted. Part 2 of then, of course, is going to be complex calcs with stoichiometry. So we've got another 2 worked examples here. Now I've made these complex in a couple of different ways, but if you just give me 2 seconds, I'll explain why. I just took a sip of coffee. I'm just needing it right now. So in this complex stoichiometry situation here, I've tried to make these a little bit more tricksy, and we're going to do a final episode that is even more tricksy again. But the idea is this. Oftentimes in an examination, I'm going to ask you a question that is difficult to understand and is difficult for you to apply your understanding. That's kind of the whole mantra of the ATAR course, and so it's good for us to get exposure to what this looks like. So we've got to consider the reaction of hydrogen with oxygen to produce water vapor. This is a really important point here. What do we need to do? We need to write an equation. It's not given to us, but we need to write it. The reaction occurs at room temperature, which is 25 degrees, and room pressure, which is 101.3 kPa, in a closed vessel. Interesting. Calculate the pressure of the resulting vessel. Interesting. So we're not talking about reactants anymore, or products. Now we're talking about the vessel itself. If 14 litres of hydrogen reacts with the perfect amount of oxygen, the vessel has a volume of 50 litres, and the final temperature is 655 degrees Celsius. Couple of major things we need to understand here. First of all, there is a chemical reaction occurring inside a closed vessel. Let's assume it's a nice cube like this. And we are trying to work out, at the beginning, there is a pressure of 101.3 kPa, and at the end, a reaction happens, temperature goes up, and we need to work out this new pressure inside this vessel. The only information we're given is that hydrogen reacts with oxygen to produce water, specifically 14 litres of hydrogen with the perfect amount, which means all of the oxygen is used up, perfect amount of that to produce a certain amount of H2O. We can assume that the H2O will fill the container. Why? Because H2O is a gas. So we can assume that we will produce 50 litres of H2O. We also know that this guy, these are our volumes. We also know the temperature of these. So we know that the temperature of this at the beginning was room temperature, which is 25 degrees Celsius, and at the end was 655 degrees Celsius. Now note how I've set out this question, right? It's different to how we would normally set out a question, and that is because it requires me to do a bit of thinking, and what is the best way for me to diagrammatically represent what it is the question is asking me to do. It's a really important skill in chemistry that we think laterally and think sideways and think, what is it that this problem is that I need to try and solve? Now, of course, 25 degrees Celsius is not helpful for us. We need to turn this into Kelvin, so we need to add 273.15 Kelvin. If I do that, I haven't actually done that in my working. I will do that in the equation, but I just doing mental math, it should be about 298.15 Kelvin. And 655 plus 273. Oh, frick, I can't do that. That's way too much, mate. way too much thinking for a grown man. 900 and something? I don't know. Let's not worry about it. But essentially, we need to move these to Kelvin because Kelvin is where we need to do. So where would I start with this question? Well, I would start by calculating my number of moles of hydrogen because that is what I know everything about. It tells me in the question here, I've got a temperature and I've got a pressure. So I can use PV equals nRT. I'm going to rearrange that equation to isolate N. So I can say that number of moles of H2 is equal to PV divided by RT, where P is equal to, 101.3 kPa, and I am trying to work it out for my final reaction. Okay, good. Let's change color so we can get some clarity as to now we're answering the question. So this was all set up here. This is all set up. Now we're answering the question. Number of moles of H2 is equal to PV divided by RT. In this circumstance, that's 101.3 times by 14. Divide that bad boy by the universal gas constant of 8.314, and then we're going to multiply that by 25 plus 273.15. And if I chuck that in a calculator, I get 0.572 moles. Part 2 of this question then, I now need to take my number of moles of H2 and work out my number of moles of H2O. So I can say here that my number of moles of H2O is equal to 2 on 2 multiplied by the number of moles of H2. Why? Due to stoich. Number of moles of H2O, I can now rearrange my PV equals nRT calc to get P equals nRT on V to isolate pressure. Why? Because the question is asking me for the pressure of the resulting vessel. I can now chuck that number in of 0.572 multiplied by 8.314 multiplied by 655 plus 273.15 because that's my temperature. Divide that all by 50 litres because it's a 50 litre vessel. And if I chuck that in a calculator, I get a very, very low pressure of 88.3 kPa. Now, what is really important for us to understand here is that I have gone through some very clear steps. The first thing I've done is calculated moles. That's my first step of what I know about. Second thing I've done is I've done some stoich. Really, really important. In any chemical reaction, we want to always do stoich, whether it's a 1-1 ratio or not. And then thirdly, I've done my final calculation. And that is the structure that we would follow for anything. So even though that question, written in a different way, presented with some different information, actually the same methodology. Okay, let's look at a different one. This time we're looking at the Haber process, which is a process for producing ammonia gas from nitrogen and hydrogen. Now, again, what's the key word here in this question is producing, which means we need to write an equation. Haber process is a process for producing ammonia gas from nitrogen and hydrogen. The reaction occurs at 500 degrees Celsius and a pressure of 35 megapascals. In one such reaction, 11,455 litres of nitrogen reacts with excess hydrogen. Calculate the volume of ammonia produced. So, first things first, let's write an equation. N2 plus H2 produces NH3. That's what our question tells us. Let's balance it. 2 and 3. So the first step in this situation here, no equation, I'm going to write the equation. Always helpful for me to have that at the very beginning. Second step, of course, is to list my knowns and unknowns. What do I know about? What do I not know about? This tells me that temperature is equal to 500 degrees Celsius. Now, of course, 500 degrees Celsius is unhelpful for me because I need that bad boy in degrees Kelvin. So 500 degrees Celsius, that is equal to actually 773.15 Kelvin because I need to add 273.15. So that's helpful. Second thing, it tells me the pressure. Pressure is equal to 35 megapascals. Megapascals is times 10 to the 3 kilopascals. So it actually is at 35,000 kPa. Really important, of course, that we make that shift because kPa is the standard unit for pressure. And then finally, we have our volume of nitrogen gas, which is 11,455 litres, and we have excess hydrogen, so we have no limiting reagent. Therefore, this is our important thing. Okay, so now we have listed everything the question tells us and everything that we know about. Is my first step going to be, now that I've done it, I need to start answering my question. I'm going to start by calculating the number of moles of N2. Why? Because my methodology says I always want to start with moles. So number of moles of N2, would you agree with me, is equal to PV divided by RT, where in this circumstance, P is equal to 35,000, V is equal to 11,455 litres. We divide all of that by R, which is 8.314, and multiply that by temperature, which is 773.15. If I chuck that in a calculator, I get a huge number of 62,371.96 moles. Excellent. I've now got my number of moles of N2, and now I can use the nuke to use the stoichiometric ratio of my equation to calculate my number of moles of ammonia, because what am I asking? Calculate volume of ammonia. So, number of moles of NH3 is equal to 2 on 1, because there's a 2 in front of ammonia and there's a 1 in front of nitrogen. So 2 on 1 multiplied by the number of moles of nitrogen, which is 62,371.96. Note here how many digits I'm carrying in my working. You always want to carry as many as you can. 124,743.91 moles. Now, generally, I'm keeping all these numbers in my calculator as I'm going so that I'm carrying as many digits as I can. I might not write all of them down. So let's confirm. Number 1, calculate the number of moles. Number 2, use the nuke to calculate a stoich ratio. And then step 3, calculate what the question is asking for, which in this circumstance is volume. And so we're going to say that the volume of NH3 is equal to a rearranged equation in the form of nRT on P, which in this circumstance, N is equal to 124,743.91, R is equal to 8.314, T is equal to 773.15, and I'm going to divide that all by pressure, which is huge, 35,000. Chuck that in a calculator. What do I get? 22,910 litres, thereabouts, of NH3. Excellent. So that's another complex stoich ratio, all done and dusted. In our next episode, we will look at how we can use the formulas of N equals V on 22.71 and PP equals nRT in some other mixed stoichiometric ratios, but that is it for now because this video has gone a long time.